Hi, we are the Department of Electrical Engineering's undergraduate RF research team. We will be presenting the bistatic radar reflectometry for real-time pavement surface condition monitoring. Students on this research team include me, Stephanie Claremont, Kang Pham, Brent Oksanen, and Rod Abusad. Pavement surface condition monitoring is an important part of monitoring our critical infrastructures and ensures safe operations. For example, the formation of ice on roads and bridges presents a significant safety issue during winter weather travel. Currently, the state-of-the-art real-time pavement surface monitoring involves applying sensors into the structures which we want to monitor. While these embedded sensor systems provide site-specific measurements, they are costly to deploy and operate, less robust, and have limited coverage/monitoring area. This project proposes to develop a bistatic radar reflectometry system for real-time pavement surface condition monitoring that can be scaled to provide large measurement area with capabilities to provide cost-effective, long-term measurements and can operate in harsh environments. This project builds on ongoing research and theoretical modeling of polarimetric wave scattering from surfaces and random media such as pavement and soil surfaces, bistatic radar signal processing and imaging, and physics-based parametric retrieval algorithms. The proposed system consists of a bistatic micro-radar reflectometry system which has displaced transmitter and receiver arranged on an incident plane. The system is also composed of a physics-based parametric retrieval algorithm for pavement surface roughness and condition estimation.
Hi, my name is Brent Oksanen. I'm here to talk about the theoretical portion of our research. So our research proposes a radar solution to monitor pavement conditions. This will be done through reflectometry. Simply, reflectometry is a method to determine the properties of the scattering surface, in our case ice, through the received signal. Our plan is to detect the difference in reflection for vertically and horizontally polarized waves. This is useful for detection because there is an angle called the Brewster angle where the vertically polarized reflections are nearly zero. For ice, the Brewster angle is about 60 degrees away from normal incidence. This means that we can detect an ice layer through measuring vertical and horizontal polarizations.
Hi, my name is Rod. I did computer simulations of our transmitting Vivaldi antenna in HFSS. As you can see, this is the antenna I designed at different angles, and the green L on the underside of the antenna is a feed line that is excited as a wave port. Next, here is the simulated VSWR plot compared against the VSWR plot of the datasheet of the transmitting antenna. And as you can see, they roughly match. And after exporting the graph into an Excel sheet, we found that we had a simulated VSWR of 1.71, which validates the VSWR of 1.58 on the datasheet. VSWR is important because an antenna having a VSWR of 2 roughly correlates to 90% of the power being transmitted. So it's important for all antennas to be less than 2.
Hi, I'm Kang. So for our reflectometry model, we have to have a bistatic radar configuration because we want to vary the angle of reflection between our transmit and receive antenna. So let's get into the system for that setup. Here we have a generator that generates a signal to be sent to our attenuator, which is then amplified and then split so that we can send one of those splits to our transmit antenna, which is our Vivaldi. And then the other split is going to go to a mixer, which mixes the transmit signal and our receive signal from our receive antenna all the way over there. And then the output of that mixer is going to be filtered and sent to a laptop, but in our case, we're going to be using a oscilloscope to be testing just so that we can show functionality of the system. Just to show that our system is actually working, here is our receive antenna receiving the same polarization of our transmitted. Now here is what happens when we flip it 90 degrees, so it's receiving different polarization. And now here's what happens when we completely point the receive antenna away from our transmit.
with results from theoretical calculation done within the Python program, simulations seen within ANSYS's high-frequency simulation software, and extensive testing done within lab, the radar reflectometry system was proven to be functional and usable for practical applications. Radar can be used to monitor surface conditions of a large area, and with further development and extensive testing, system performance can be optimized and possibly the radar system can be widely implemented.